the notion of time is the progression of computation. So something, we say this event happens and this other event can only happen after that first event, later in time than that first event, because that second event is using the output from the first event. It's consuming the kind of atoms of space that were created in that first event.
Welcome to Close to the Truth. I'm speaking with Stephen Wolfram, the distinguished physicist, computer scientist, and software entrepreneur. We're discussing in depth the Wolfram Physics Project, Stephen's grand, indeed radical vision of a new kind of science in which computation via simple rules is the foundation of physical reality. The Wolfram Physics Project is a Close to the Truth multi-part series. This is part 3 on a path to a fundamental theory of physics. Stephen, let's start by giving a quick overview of the Wolfram Physics Project itself, and then we'll get into how you get to this path to a fundamental theory of physics.
So the question is, what's the universe made of? And our physics project basically says the answer is it's computation all the way down. And so let's see what that means. Essentially, the one sort of historical path we can take is back in antiquity, people were sort of wondering, what's the universe made of? Is it made of atomic discrete things? Is it made of kind of continuous flowing things, or what? By the end of the 19th century, partly that was answered. Matter is discrete. It's made of discrete molecules. A little bit later, you can think of light as being made of discrete photons. At the beginning of the 20th century, a lot of physicists assumed that space would be discrete as well, but they couldn't figure out how to make that work. In fact, they published very little about it. It's only very recently that I learnt that all the greats, basically at that time, thought that space was discrete. And even like Einstein made comments like, in the end, it will turn out that space is discrete, but we don't have the appropriate tools to see how that works yet. Well, 100 years later, I think we do. And the sort of beginning of a project is to think about what's the universe made of and what is space made of. We don't usually think of space as being made of something. We just usually think of space as being this background where we can put things here or there or anywhere. But like a fluid like water, we now know is made of molecules. So we think of space as being made of discrete atoms of space, not atoms in the sense of material atoms, but these indivisible points that we can think of as sort of the raw material of space. And kind of the starting point for thinking about what the universe is made of is to think it's this giant collection of atoms of space, where the only thing we know about atoms of space is how they're related to each other, sort of what the friends of one atom of space are. And so we can represent that at a sort of mathematical level as a graph, or actually more in the way that we set it up as a hypergraph. Hypergraph is just something where you're saying we have these points, these nodes, and we have these hyper edges in which we associate, we relate some number of nodes together. So an ordinary graph, we'd always be relating pairs of nodes. In a hypergraph, we can relate any number of nodes with a hyper edge, so to speak. So
And so this is a key point, using hypergraph, which is a representation of a computation to represent space. Is this kind of the first step in the path to the fundamental theory of physics?
It's not representing a computation. The hypergraph is just, it's kind of like if you're a computer person, it's a data structure. It's
Yeah.
the data structure of the universe, so to speak. So it is just, that is the structure of space and everything in it. So another feature of our model is that there's nothing in the universe other than space. Everything that we know, the electrons, the photons, us, and so on, it's all just features of space. So it's like if we were dealing with a fluid like water, we would say, well, there's this eddy that goes through the water. That eddy is ultimately made of molecules, just like any other feature of the fluid, but the eddy has some independent identity to it. And that's kind of the way we imagine something like an electron works in space, where the space is built up from this hypergraph. At the bottom, everything is just represented as this hypergraph. And that that everything about the universe is represented in the structure of that hypergraph.
When you say represented, do you mean represented in a modeling sense or in some ways as the reality itself?
Well, usually we're used in science to saying we make models of things, which means we're making an approximation to how something works,
Right.
where we say we capture some features and ignore other features. This is the unique case where we're trying to nail it. This is, this is the ultimate model because there's no approximation we're talking about. The idea is that this is what a representation of the way the universe works. Now, I say representation because it's it is what is the nature of a model? A model is something which is trying to translate between what the universe is actually doing and what we can understand with our minds. So when I say it's represented as a hypergraph, that's the way that we can conceptualize what's going on. If we say, in some sense, what is actually there, it's that's sort of that's a different kind of thing. That's not. It's like saying we have Newtonian, the equations of mechanics from the calculus equations that Newton produced, and we say the Earth is moving according to this law of gravity and so on. We don't imagine that the Earth has a computer inside it that is solving those
Yeah.
equations. We imagine that those equations are representing what the Earth does, and this is the same kind of thing with the difference that instead of saying this is an approximation to what's going on, we're saying this is the whole story of what's going on. And so, the first step is to think about sort of the structure of space and everything in space. The next question is, so what happens with this? How does time work? This is the static structure of space. How does this progress through time? And the idea is that this network, this hypergraph, at every moment pieces of that hypergraph are being rewritten into other pieces of hypergraph. So the basic thing is that there are rules that say if you see a piece of hypergraph that looks like this, it will be rewritten as a piece of hypergraph that looks like that. And that's happening all the time. That is the progress of time is the the progressive rewriting of this hypergraph. And that's kind of the story of what the universe is and what it does is the hypergraph and the rewriting of this hypergraph.
Okay, so this is a very powerful idea. It's actually quite easy to understand the way you just described it, as the space is the hypergraph, and the rewriting of the hypergraph into new structures is the progressing of time and what we see as events, whether they're micro or macro. So just to get a sense of orders of magnitude, if this is at all possible, of how you would describe. I mean, we know the size of the observable universe, at least, I don't know, 10 to the 26 meters or whatever. We know plankton, Planck lengths, and Planck times, 10 to the minus 43rd or 10 to the minus 27, various elements that we think are the simple. So putting this together, what kind of orders of magnitude can you describe in terms of the actual hypergraph of the universe, if to represent it and
Yeah, right.
using in your sense, and the number of rules, order of magnitude that you would need in order to make all the transformations necessary?
So, okay, in terms of, what is the elementary length? If we were to convert kind of the kind of one edge of a hypergraph
Yeah,
into meters, how many meters would it be?
right.
We don't know. There's in our model, there's one parameter. It's the elementary length, the elementary time, the elementary energy. It's also related to a thing we call the maximum entanglement speed, which we'll get onto when we talk about quantum mechanics. But we don't know the value of this. I have a very vague estimate that it might be around 10 to the minus 100 meters, that the
Oh,
elementary length might be around 10 to the minus 100 meters. It's much smaller than the Planck scale.
much smaller than the Planck line.
Right. And
And
it,
and
it,
ha
it kind of resolves a bit of a mystery, which is the Planck energy is actually quite macroscopic in the usual setup. Our elementary energy is also microscopic. which
Okay.
is kind of the way you would expect it to be. So, there's a question of will we be lucky enough that there's an experiment that we can do or that even has been done that will detect the elementary length.
Yeah,
So in other words,
that sounds very improbable.
well, let me explain why it's not quite so improbable. Okay, so I think people were really lucky at the beginning of the 20th century that molecules were as big as they are relative to the kinds of equipment that existed to make measurements at the time.
Yeah.
But even despite that, actually they could have known molecules existed earlier because Brownian motion, which was the thing that kind of clinched the whole story, that was discovered in 1827. So all the time that people like Boltzmann were worrying about do molecules exist or not, actually there was already evidence that they existed. It's just it wasn't interpreted right. I will be, I think it is very likely that there was already data in astrophysics, in various areas of quantum mechanics, that already is a clue that there's discreteness to space, but it hasn't been interpreted yet. And that's an interesting project to try and sort of mine the literature before you spend tens of billions of dollars building experiments to look for the next thing. But what happens is that there are some effects that are predicted by a kind of model that are very different from what's been seen before. So here's an example of one. So when you have this big hypergraph, it does not define what the dimensionality of space is. We normally think space is this thing that we can describe with three coordinates and it's three dimensions and so on. But this hypergraph, it doesn't have any fixed set of coordinates. It's what emerges when you have a big enough hypergraph is something which can approximate space, but at the beginning, it's not defined whether that space is two-dimensional or three-dimensional or 3.1 dimensional or infinite dimensional or whatever else. And so it's one of the things that we expect are dimension fluctuations, where the dimensionality of space is not exactly three. That's a bizarre phenomenon.
It
Its
is.
mathematical analysis is difficult. I mean, people study, they study calculus of one variable, they study calculus of two or three variables. They don't study calculus of 2.7 variables because nobody knows how that works.
All right.
And we have to we're kind of trying to rebuild the sort of the whole tower of geometry and calculus and so on when for what you build on top of these hypergraphs rather than on top of kind of Euclid's version of space.
Okay,
So
so
that's an,
let's go then and get back to what you said. Give you your 10 to the minus hundredth is the ultimate point structure of space. Nice round number we can easily
yeah.
remember. What are the implications of that given the size of the known universe in terms of the hypergraphic representation?
Well, I mean, it's the first question is when you have this hypergraph and it's sort of doing its thing at this discrete level, what what does it do on the scale of human experience, so to speak, or on the scale of astronomy? It's a similar question to asking if you have a fluid that's made of a bunch of molecules, you've got all these molecules bouncing around, what is the large scale aggregate behavior of the fluid? What we know in that case is that the large scale aggregate behavior follows the equations of fluid mechanics. And so one question is, well, what is the large scale aggregate behavior that we see from this hypergraph doing all its rewriting at this very small scale? The answer is Einstein's equations for the structure of space-time. So what is, in the case of fluid mechanics, for molecular dynamics, we can derive the Navier-Stokes equations of fluid flow. From this hypergraph rewriting, we can derive, and when I say derive, mathematicians will say there are many, many footnotes. There's a century worth of footnotes that still has to be filled in to see how that derivation works. By the way, the same is even true for fluid mechanics. The derivation of fluid mechanics from molecular dynamics has never been done in a mathematically rigorous way.
Hmm.
But we can, one of the great advantages that I've had methodologically in the things that I've done is that there is both the mathematics side of analyzing things, but also there's computer experiments. And you can see a lot of what's true from computer experiments, even though you can't necessarily say, here's how I can give the full sort of mathematical narrative for how this works. But so the first thing to say is that the kind of large scale behavior of space-time is that you get from this underlying hypergraph rewriting follows the Einstein equations, but it has some deviations like these dimension fluctuations and so on. The
Hmm.
other thing that happens is that a lot of features of physics that one has just had to say, oh, well, you follow the equations, you solve the equations, then you work out how things will work. A lot of features of physics now become things that you can kind of almost mechanically explain. Let me give an example. So in relativity, one of the sort of classic phenomena is time dilation. When things move more quickly, time seems to run slower for them. Well, in our physics project, we can really see quite mechanically why that happens. So if you have a thing, like an electron, let's say, and it's represented by some structure in the hypergraph, and it is progressively it continues to exist because as the hypergraph gets rewritten, that electron structure is preserved by the successive rewritings. It's recreated at every moment in time by this hypergraph rewriting process. Now we say, let's have the electron move from here to there. What happens is some of its sort of computation budget, if it's moving, has to be used in kind of recreating the electron at different places in space. So if it's using some of its computation budget to recreate itself at different places in space, it has less computation budget to just sort of be continuing through time. So in effect, it's used up its computation budget on motion, so its time has to run slower for it. It has
Oh,
less computation budget to sort of run itself forward in time.
and
But
that assumes there's a finite computation budget.
yes, but the whole point is that the whole notion of time is that time is associated with the progressive doing of computation. Our what happens in the universe, in a sense, we experience time because computations are going on in us, and we are. But if you were to just look from outside the universe, you could say, well, I'm just not going to do the next step of computation. Then the universe is frozen, but so are we. Our perception of the
Hmm.
passage of time is a consequence of the fact that these computations are going on in us as in the rest of the universe. The fact that there is a sort of uniformity to that computation, both inside us and in the universe at large, is why there is a sort of invariant notion of time. It could be the case that time was very different for different kinds of entities. But the fact is that, in a sense, it comes back to the principle of computational equivalence, actually, that there is a sort of a uniform notion of time that applies both to our experience of time and to what happens in time in the universe at large.
Let's take a simpler example from classical physics, energy and momentum, have been thought to be understandable in Newtonian physics. How would those represent to get to see how the hypergraph system works for physics in a simple way?
Right. So, well, I didn't think energy was going to be simple, actually. I
Uh-huh.
thought we were going to have to understand particles in order to understand energy. I was
Uh-huh.
wrong. Turns out that we can think about energy as a bulk phenomenon. And roughly, energy is the density of activity in the hypergraph. So roughly, the and momentum. So put a little bit more precisely, the way that one thinks about things is every rewriting event is an event, and you think about all these different rewriting events, and they have a certain network of causal relationships. So one rewriting event has to have happened before another one can happen because the next one is going to use the output from the first one. And that builds one up, this kind of causal graph of causal connections between these rewriting events.
Hmm.
And so, put a little bit more formally, energy is essentially the flux of causal edges through what we can call space-like hypersurfaces.
Hmm.
So, it's kind of like the way that this is one of the tricky things which was not known when people were thinking about sort of discrete space in the early part of the 20th century. What was not known, people were imagining that space would have to be some sort of discrete lattice or something. What emerges in the physics project is that the key thing to look at is this causal graph of the causal relationships between different events. And it's invariances of that causal graph that lead to relativity,
Hmm.
that lead to the fact that the notion of time is the progression of computation. So something we say this event happens and this other event can only happen after that first event, later in time than that first event, because that second event is using the output from the first event. It's consuming the kind of atoms of space that were created in that first event. Now, what can happen is there are all these events taking place, and you can say, well, which events can we think of as simultaneous? And this is very similar to the kind of way one thinks about relativity. One says, what events can one think of as a space-like surface, as events that can be thought of as just laid out in space all at the same time? And there are many different possible choices of space-like surfaces, many different choices of simultaneity surfaces. That's the same kind of thing that happens in relativity, but it happens very directly in our models. And it's that and the sort of the key thing that one's looking at is this causal graph. Energy turns out to be the flux of causal edges through space-like hypersurfaces. Momentum is a flux through time-like hypersurfaces. Those are sort of the formal statements. I would say that one of the things that was a mystery for a long time is why in relativity theory the transformation rules for space and time have the same mathematical form as the transformation rules for energy and momentum.
Hmm.
In our model, it's obvious why that's the case. I
Yeah,
mean,
that
from what I
that
just said, it's not
that,
so
that
obvious, but
that's an interesting point because that is the case. I mean, in your model, they're both related to the same kind of structure, so it's almost trivial because they're both caused by the same transformations of hypergraph as opposed to two radically different kinds of things.
right.
Let me go back to an earlier question. So we got an order of magnitude of the nature of the hypergraph by 10 to the minus 100th, and we know the size of the universe, at least observable universe. Let's go to the order of magnitude of the number or kinds of transformations or the rules that cause these transformations in the hypergraph, which generates the physics that we know. How many different kinds of rules do you need?
Okay, we're now about to descend into the deeper parts of the rabbit hole because the that's ultimately the story of the Rulliad.
All right, well,
Because
we're going to do the Rulliad in another
right, so
complete
I
in
think we should
detail.
not let me just
Okay.
say that for our there are many different rules that we can use to describe how a universe works. And they are all ultimately equivalent in terms of the things that we observe about the universe. And let me give a way to sort of see why that might work that way. It relates again to fluid mechanics. If we look at the equations of fluid mechanics, it's the same equations for water and for air, even though the molecules that make up water and air are quite
Yeah.
different.
All right. No
And
teaching.
it's but it is a bit more complicated in the full case of the universe because we are observers embedded within the thing that is the universe. And so if we're when we say we are thinking about the universe in this way in terms of these rules, but we are also made of those rules. And it turns out that it we can attribute sort of the behavior of the universe to different rules and end up coming to the same conclusions about the aspects of the universe that are observable. So I think the way to answer that is to say there actually can be just one rule that or a very small number of rules that we can run those rules and get what is at our observable to us as what happens in the universe. So let me give an example of that. I mean, so we have simulations now of things like black hole mergers in our models, and the you can use a whole range of different possible rules, and you'll always get the same kind of behavior at the scale. If you look at the absolutely microscopic scale, you'll see different things going on. But if you look at a sort of zoomed out scale, you'll see these black holes merging and some gravitational waves produced and so on. And it's so that's it's a slightly weird thing because it's a little different from the way that one's thought about physical theories before, and that will take us into the story of the Rulliad.
Okay,
But
well, Rulliad's coming soon. So this is great. Viewers can watch all the videos in Closer to Truth, the Wolfram Physics Project on the Closer to Truth website and YouTube channel, and including the Rulliad, which is coming, which is going to be, I think, my favorite. Thanks for joining us. Thank you for watching. If you like this video, please like and comment below. You can support Closer to Truth by subscribing. Closer to Truth is now accepting your tax-exempt donations. Please come to closertotruth.com/donate. Thank you very much for supporting us, and thanks for watching.